in some respects continue on some of the themes that Victor spoke about, but in slightly different form, different aspect ratio. I'm going to concentrate on the electronic, optical, thermal properties of nitride nanowires, and then if there's a little bit of time, I'll talk about a couple of other topics that I think will be of interest to the people gathered here, particularly given the emphasis of plasmonics yesterday and this morning's talk on using molecular electronics, possibly of molecules for thermoelectrics. So just a brief outline. I'll talk about a little bit about motivation. I'll talk about nanowire growth, the different modes, different ways that we're using to grow nanowires. I'll talk about electrical transport and how that relates to dimension, how it relates to synthesis conditions. I'll talk about photoluminescence and how that relates to electrical properties as well as growth on individual nanowires. I'll talk about thermal transport and thermal breakdown. And finally, I'll talk about nanowire lasers. Motivation, well, there's a lot of motivations. Nanowires, of course, particularly with respect to nitrides, have very low defect density. I'll show some of that. Their growth is compatible with a variety of substrates, including silicon, so it gives you the opportunity for integration of direct band gap materials with silicon. And of course, as Victor was pointing out, there's a lot of unique optical and electrical properties when you get down to small dimensions. We're not always quite to those dimensions, but it's useful to keep that in mind, as that can give enhanced optical properties. Of course, nitrides are very interesting. They have a band gap that can span all the way from near IR to hard UV, very high breakdown field, saturation velocity that is more than twice that of gallium arsenide. Mobility is lower, but the saturation velocity is very high. High thermal conductivity and chemical inertness. Challenges, not just with nitride nanowires, but I think some of those challenges are harder with nitride nanowires, is to control the growth, to determine the location, the position, the dimensions, and the properties of the nitrides, as well as still the fundamental understanding of how these materials behave when we have high surface to volume ratio, when contacts can behave differently because of reduced dimensions, metallurgical reactions that can take up a large volume of the material. So just very briefly, some of the potential applications, particularly for nitrides, like high-frequency oscillators. In this case, the relaxation time of electrons in gallium nitride from the satellite valley to gamma valley is a lot faster than in gallium arsenide. So one could potentially have oscillators that operate high frequency, but previously these devices have been hampered by high defect density. And as I'll show, the nanowires are promising in that respect that they have very low defect density. And then we'll be talking about lasing, but this is something that, of course, resonates with what Victor was talking about, that as you reduce the dimensions, the density of states works to your advantage. So there's less waste of electrons going into higher states and then just giving that energy off to phonons. Of course, nanowires are different from quantum dots, so you might say, well, quantum dots are better, but as I'll show later on in my talk, one possible advantage for nanowires is that in that case, the nanowire itself forms the cavity, whereas with quantum dots, you have to form the cavity. And the other thing is that nanowires, again, as I'll show, can be grown with extreme precision and extreme uniformity, so that there's very little spread in dimensions. And finally, of course, once one grows a nanowire, one can grow a quantum well structure around it to get some of the benefits from the reduced dimension, or further reduced dimensionality. And so I will be talking about lasing. I'll talk a lot more about it. Here's kind of just as a kind of to whet your appetite, some recent data from nanowires grown at University of New Mexico by Steve Burson. and I'll talk a lot more about it. So let me talk about growth. I think virtually everybody here probably heard about VLS, growth, vapor, liquid, solid. I don't actually believe it's vapor, liquid, solid. I think a lot of evidence right now is that it's actually vapor, solid, solid. But
that's for 3.5s.
For 3.5s, yes, yeah, right, absolutely, yeah. Yes. So I think for 3.5s, this is what we see with actually gallium arsenide. It's what we see with gallium nitride. But the basic growth goes as a catalyst metal. Often it's nickel. We're now also exploring other metals that have both lower and higher melting temperature than nickel. I'll explain why we're doing that. But a lot of the work I'll show you for this type of growth is done with nickel. So the catalyst is dispersed on the surface. The trimethyl gallium and ammonia, in our case, which is MOCVD growth, are brought in a CVD reactor, and they saturate the catalyst metal, and a single crystal nanowire precipitates. You can see the catalyst particle. I'll show you some three-dimensional images that are reconstructed from scanning tunneling electron microscopy tomography, so you'll have a better view of what these nanowires look like. Once the nanowire is grown, one can then introduce, for example, trimethyl indium or trimethyl aluminum and ammonia, and grow a core shell nanowire, and you see a cross-section right there.
What substrates you use?
I'll talk about substrates actually in a few slides. So, but generally we use silicon, we use sapphire and different orientation of sapphire. We use silicon dioxide. So those are the prototypical substrates. People have used aluminum, just polycrystalline aluminum, and the nanowires are, in virtually all cases when grown this method, are single crystalline, but they don't always have the same orientation in terms of orientation in space, or in terms of crystallographic orientation. Now, just very briefly, as I mentioned, so one of the nice things about VLS is that, or VSS, is that the catalyst diameter influences a great deal what the nanowire diameter is, and I'll show you in a few slides that the catalyst diameter, that's what you see right here, can actually be defined using nanoelectron lithography to give you much more control over the diameter. But this is just an example where a smaller catalyst particle leads to finer nanowires. The black line there is a 1 micron in all cases. Victor, you were asking about substrates. So substrate orientation does play an effect. So even though the mechanism here is precipitation out of a catalyst, there is some epitaxial relationship with the substrate. And that's very evident, for example, when we use, here you see 3 different orientations of sapphire, and particularly the R phase, the 1 bar, O2, you see that there's the nanowires are almost all vertical, and if you look closely, I'll show you in a minute, they're all oriented in plane. And we can actually understand that by looking at the unit cell of 1 bar O2 sapphire and the A plane of gallium nitride. We see that there is only about a little over 1% lattice mismatch, and that's a pretty good explanation why we see this orientation. And one can, of course, think of a lot of applications in this case if all the nanowires are truly oriented, not only vertically, but also oriented in plane. One can try to do overgrowth and make a continuous film. But this is an example where the substrate does influence it. And just to tell you kind of the directions that we're heading in is, for example, to look at highly textured metallic substrates, because I think one of the really learning advantages of this kind of growth is that you could get single crystal on a polycrystalline or amorphous substrate. That gives you the ability to dream that you can do 3-dimensional circuit assembly. Whereas right now, once you get in a CMOS, only at the first level, everything is single crystal, but if you want to try to make a transistor on top of an oxide, it's already amorphous silicon or polycrystalline, and of course the mobility is greatly reduced. And so we're looking at highly textured, oriented metallic films to see if we can still get highly oriented nanowire growth. Here's an example. Now, in this case, this is gallium arsenide nanowire growth, and this is on 111 gallium arsenide. What we see in this case is that these nanowires that are also, in this case, of course, gallium arsenide is FCC, so we're no longer dealing with quartzite. But I wanted to show you this example where we indeed have growth. If you actually look carefully where these nanowires are originating, they're all 111, but of course there's several 111 directions. There are 4 equivalent 111 directions. And so, but if you look at where these nanowires are originating, the spacing is exactly the same as that determined by, in this case, this is gold catalyst patterned on 111 gallium arsenide. And we see similar behavior with silicon and germanium nanowires. And in this case, the germanium nanowires were grown on 100 silicon, but here you see the catalyst. You don't see nanowire growth in every catalyst, but generally it is where the catalyst is placed. And the nanowire diameter, you can see how the catalyst balled up, is very reproducible, as well as in this case. In this case, what we did is put catalyst metal inside of a well, and you see a very narrow distribution of nanowires. Now, this is in the case of silicon and germanium, so we use silane and germane as the feeder gas. Of course, we wanted to do the same thing with gallium nitride. In other words, instead of just growing just a forest of nanowires, we'd like to decide what location the nanowire is going to be. Let me just, I'll just forward to that. And then I'll go back, because I didn't realize the slides were not in that order. But this is what happens when we try to grow on a patterned substrate the gallium nitride, and what we see is that it was there's a lot of polycrystalline material with some nanowires growing. What we think is happening is that in this case the trimethyl gallium and ammonia crack and provide growth at the temperature at which you're growing, which is quite high, 900 degrees C. So we're already able to crack those gases, and there's polycrystalline material growth as well as nanowire growth. So one of the things that we wanted to do is maybe to reduce the temperature so that there will be only catalyzed nanowire growth. But so to reduce the temperature, we have to go to a different metal. In this case, gold. And this is a very, very recent result where we're starting to see, under certain conditions, this was just a film of gold, that we're getting something that looks like a nanowire without having kind of just a polycrystalline mess of material. So we're looking at ways to get MOCVD growth of nanowires without polycrystalline film. So let me just back up here, and just to show you that from TEM analysis, these nanowires are indeed single crystalline. They have extremely low dislocation density, but it is not true to say that they have no defects. They are, for example, stacking faults. But stacking faults are frequently much less active electrically than dislocations. So, it is expected that these nanowires will perform better electrically and optically. And as I promised, now I think I'm going to have to come out of it. These are, just to give you a better view, this is what these nanowires look like. So what you see in blue is the catalyst. Now this is, in fact, not simply a gallium nitride, but this is gallium nitride or aluminum nitride. You can actually see the aluminum nitride. And the other thing that we're kind of surprised is that certainly at the larger diameters, these nanowires are almost perfect equilateral triangles. But at this dimension, they're actually, you can see they're not perfect triangles. And also, obviously the catalyst is there. It is often off to the side, but sometimes it is straight on, and it just varies from nanowire to nanowire. Okay, so I was telling you about metal catalyzed growth. But one doesn't have to rely on metal catalyzed growth. Of course, there's concern that does the catalyst dissolve to some extent, and I think it does dissolve to some extent in the nanowire, although if one picks the temperature and solubility carefully, one can maintain that solubility to a really, really small amount. But there is a way to grow nanowires, or these are probably better called nanopillars, without using any catalyst metal. Of course, in this case, what we're doing is we're putting gallium nitride either on silicon carbide or sapphire, and then patterning a mask. This mask, in this case, silicon nitride. Silicon nitride can also work. These are going by MOCVD, and you can see that basically the mask defines the nanopillar dimensions. And when in some cases they're perfect hexagons. In this case, you can see they're not perfect hexagons. And one can do that also with gallium arsenite. And these are grown by Diana Huffaker, also from UNM. And we're very interested in these materials for a variety of applications, not only in terms of vertical nano laser array, but possibly also for as a Schottky detector. So there's a lot of possibilities when you can grow these very perfect pillars. So yes.
What are the dimensions on those?
Okay, so I'm sorry, I should have. So these are about 200 nanometers in dimension. So this whole line here is 1 micron. Okay, and this really is determined by the mask. So if you can make the mold smaller, you'll get smaller growth. Now I use nano imprint lithography to pattern. The nano imprint lithography mold can be fabricated by e-beam lithography, and that's what we're doing right now. Just using, for example, e-beam lithography to start making different dimensions to make a mold, which can then be used to pattern the substrate for subsequent nanopillar and nanowire growth. And I'll get back and I'll talk about electrical and optical properties of these nanowires. But now I'm going to talk about the electrical properties, and I'll go back and first talk about the VLS growing ones. Okay, so you get this mess of nanowires, and you say, well, how do you measure them? Of course, we'd like to measure them on an individual basis. So what we did a few years ago is we developed what we call a platform. It's a simple design, a bunch of interdigitated electrodes. Each electrode is addressable. We disperse the nanowires. We don't use e-beam lithography, so it's very quick. One can make lots of devices in one run, provided that they're longer than, let's say, a micron, and preferably are about 3 microns, and we get high yield. In this case, you're looking at nickel-gold electrodes that have been alloyed. That's why you see kind of this kind of pattern. And I'll show you that that's how we form ohmic contacts to these nanowires. This is just an example where you see the IV is deposited. It's clearly not ohmic, and then after it's been annealed, it's a nice straight line. And we're actually getting resistances that are getting to be below 1 × 10⁻⁴ ohm centimeters squared. And maybe even getting close to 1 × 10⁻⁵, which is, I think, decent. Now, in many cases, actually virtually all cases, these nanowires are N-type. How do we know that? Well, of course, our substrate is silicon with an oxide. We can use the gate. We can use the silicon as a gate electrode. It's generally degeneratively doped, and many people do that, and they use the transistor characteristics, the source drain current versus gate bias, to extract things like mobility out of the transconductance, which I think is a mistake. And the reason it's a mistake, particularly in this kind of simple geometry, is that, as you see, there's a lot of surface states. And in fact, just if you can see this, if you're familiar with transistor characteristics, you see this is really bad. It's not always that bad, but I picked this example to show you how bad it can be. There's a huge hysteresis, okay, which means that there are some other things on the surface that are charging and discharging, and they're causing this hysteresis. It's a clear sign that there are surface states. And of course, if my bias is going not just to move let's say the bands relative to the Fermi level, but also goes into charging states, then the transconductance that I'm getting is really meaningless. And so there's no sense in calculating mobility, which is going to be a lot lower than what it truly is. And so one has to be very careful in making sure that there's a good either gate dielectric or what we're trying to do right now, for example, form a MESFET. But it does show that they are N-type. Okay, so as formed, they are N-type. We can furthermore, what we can do is we can look at the resistance of the nanowires as a function of dimension. I have showed you already that by doing this metallization, we get on larger diameter, we get nice ohmic contacts. However, what we see is that as the dimension, as the width of the nanowire decreases below about 100 nanometers, the resistance shoots up very, very sharply. And in fact, if you notice, this is on a log plot. So if you consider that your resistance is, let's say, 2 times the contact resistance, contact resistance will go approximately as the area of the contact, which will go linearly with the width, okay, and depends on the diameter, which will go as a square of the width, okay. Then on a log plot, both of those will be linear, right? Because I'm going to take a log, and so that's what we see here is a linear behavior. But as we get below about 100 nanometers, we see that it becomes very, very resistant. And we can explain that in a very simple way. So people have measured for bulk gallium nitride that there are surface states, and depending on who did the measurements, they're anywhere from about 0.55 eV to maybe closer to an EV. So if we assume that we have surface states that I'll say 1 EV below the conduction band edge, then we can actually try to estimate what's going to be the depletion width using just a linear model. What you see here, this is the plot right here, where I plotted the electron concentration density, okay, which in S-grown undoped gallium nitride is typically something on 1e to the 17th. And then I've plotted here the minimum surface state density per centimeter squared required to accept those carriers. Okay, because what you have is you have carriers in the bulk, they find some surface state that go into the surface state, right? And what we find is that in fact, at 1e to the 17th, okay, if we have a surface state density of 1e to the 12th, the nanowire will be completely depleted, and it comes out right at 100 nanometers. Now, of course, this is a very simplistic calculation. I don't know exactly what my carrier density is, but it gives a pretty good feeling that indeed it is very feasible that these nanowires will be depleted. And in fact, what I'll show you, and I'll show you some of our data, but this was already kind of hypothesized just based on the switching speed. When you look at photoconductivity of gallium nitride nanowires, when their diameter is very small, it's very fast. And you can understand that if it's very small, right, and there's always going to be if there's surface state, there's always going to be a bending, right? But if it's very wide, then the carriers are going to be separated. So it takes them a long time to recombine, and so that they're very, very small. And so it takes a long time to recombine, so the response is very slow, and they're very conducting. When the diameter is small, they're very resistive, but they're very fast. That is actually kind of a useful thing. I'll go back to the other slide in a second. I guess I somehow missed a slide in here. Well, what I was going to show you is that you can make a very nice photoconductor using this principle. After the talk, if you stop, I'll show you. I want what you do with the slide. But the fact that they're depleted, their dark current is very low. So if you have a photoconductor sitting, it's not wasting any energy because they're really, really resistant. Maybe in the other talk, I'll open another presentation where I have that slide. The other thing is that not only does the depletion can lead to high resistance, as the diameter of the nanowire decreases, particularly as it decreases below what would be the depletion width, given a certain Schottky barrier, which is on the order of an EV, then what happens is that the bands can bend underneath the metal contact sufficiently. And what that results in is, in fact, the resistance is going to be higher. Because you have to think, how do we form ohmic contacts? In most cases, we don't actually form an ohmic contact because of band alignment. Unless you're talking about indium arsenite or gallium arsenite, you have a graded junction. In virtually all cases, what we're doing is we're reacting with one of the components of the semiconductor. For example, it could be forming a nitride, like extracting some of the nitrogen. For example, pi makes a good ohmic contact, which creates kind of an N+ region, or a heavily doped region, and so the electrons can tunnel through it. But if the dimension is very small, then the bands can't bend completely. And so then it becomes very hard to tunnel through it, and that can also lead to higher contact resistance.
Ali,
Yes.
has anyone tried passivating these wires, like using the same tricks they use with quantum dots?
Absolutely. That was actually the slide here. So what I showed you earlier is that for neat gallium nitride, without any coating on it, they become completely resistive at dimensions below 100 nanometers, at least for our type growth. However, when we put aluminum nitride over them, then even at a total thickness of 52 nanometers, so you can see that the gallium nitride itself is even smaller. They are not only conductive, but they can be, you can see, even with our thick oxide underneath the thick oxide in the silicon, we can actually turn them on and off reproducibly. So absolutely, one can passivate. And so aluminum nitride is one way to passivate, because aluminum nitride is high band gap, of course, and so yes, absolutely that works. So now, what I was just telling you about the electrical properties of these nanowires. We're also very interested in optical properties and how they relate to growth and the electrical properties. And so what we do is we just use microphotoluminescence. So we have a probe station and micro-PL using a helium-cadmium laser. So, and of course, our platform is ideal for zeroing in on the nanowire. You can see the photoluminescence image here, and you can see the spectrum right there. And so what we can start doing is, first of all, we can look at a nanowire along its length. In this case, you see how the peaks shift. We're observing this kind of behavior. We don't completely understand it. You can see there's also splitting. But it gives you this ability to look at a portion of a nanowire, look at its electrical properties, and look at its photoluminescence. And what we can start doing is looking at different nanowires that were grown under, in this case, different substrate temperature, and looking at how their photoluminescence changes and how their resistance changes. Now, as I mentioned, what we do is we use MOCVD, meaning that we have a source of carbon. A number of people don't use MOCVD. They just flow ammonia over a little container of gallium that's placed upstream from their susceptor. And so the ammonia reacts with the gallium, transports to the susceptor, there is a catalyst, and a nanowire growth. Mark Reed group did extensive studies of these nanowires. They found that there's almost no change in conductivity, whether or not you grow at 800, 900, 1,000 degrees. No change. We find orders of magnitude change when you go from, let's say, 800 to 900 degrees C. You go from being very resistive to much more conductive. And this is all for nanowires larger than 300 nanometers. So we're not talking about small nanowires that are depleted. Okay, I want to get that. That's why there's fewer data points. They're all about 300 nanometers in diameter. And what we see here is that as the temperature increases, as you go particularly from 800 to 900, the level of yellow luminescence, which is associated with defects, the ratio of yellow luminescence, the fraction of yellow luminescence decreases substantially. This is this region right here. And the conductivity becomes much higher, as opposed to nanowires grown at lower temperature, which have very high yellow luminescence and are very resistant. So what we think is happening is that carbon, because that's the big difference between our growth, we use MOCVD, and people that don't use MOCVD, they don't use a carbon precursor, carbon gets incorporated. Carbon has been associated or linked or theorized to be linked with a deep acceptor. And so what it does is simply compensates the intrinsic N-type nanowires, and that's why they're so resistant. Okay? Oh, this is the slide. So I don't know how I think I was meddling around. So here you're seeing a nanowire that's fully depleted, but when we shine essentially nanowatts of power, very low UV power on this nanowire, we see that it's the current. This is a single nanowire, and we packaged it because there's some people at San Diego. This is one of the things that people are interested in photodetectors, particularly if they have low dark current, because you'd like to get away from things like photomultiplier tubes. So we completely packaged it, and what you're seeing here is, in this case, I was just switching with the laser shutter on and off. So I don't know how fast it really is, except that it has very, very low, essentially almost no dark current. This is at 1 volt bias, and of course, when we shine the light, there's a lot of current on it. Okay, so as I mentioned, we're interested in making things like lasers. Lasers require a lot of power. So not only so they don't break down, but of course you don't want the wavelength to change. So thermal management is very important. Well, doing thermal measurements is difficult. I've never done it. Okay, so people talk about this 3 omega measurement, and to me it's like, well, I've never done it. But I'm very interested in the thermal transport characteristics. So what we decided to do, since we can look at photoluminescence, we can measure the band gap, and therefore we can measure the temperature, because it's very well known, very well established, how the band gap varies with temperature. And in fact, what we decided to do is to start passing current under steady state conditions. So we apply a voltage, a DC voltage, we know what the current is, we hold it for 10 minutes, that's what you see here, okay? You can see that the starting temperature is already not room temperature. Of course, I'm shining a laser on it, right? So it is heating up. That's understandable. You can see that, but as we apply more voltage, that's what you see in green. Blue is the current. What you're seeing is that the temperature rises. Okay. And this is just an example of a nanowire with photoluminescence. It's the same nanowire. And so we can actually plot the measured temperature versus the DC power. And it's linear. I'm only showing a few nanowires. We're actually done more than that. And I came to one of my colleagues, Rhys Jones, who does finite element calculations and thermal management. He said, well, this is what I can measure. I know that there's probably going to be conduction into the contacts, some conduction probably through the SiO2 into the silicon. Okay, of course, SiO2 is not a very conductor. Some convection, some emission. So can we, since we know that we are under steady state conditions, we know how the temperature varies with the power input, can we extract the temperature profile, can we extract the thermal conductivity? And this is what we've done. Based on that, this is just some results of thermal simulation. We in fact estimated what convection, how much emission based on the emissivity of gallium nitride, and I can tell you that these losses, okay, to temperature, are much less than the conduction through the nanowire to the metal contacts on it. That really, really does dominate. And so we can actually start extracting the thermal conductivity. And when we do that, what we find, again, this is 4 nanowires that are certainly larger than 200 nanometers. If I go back, I plotted some of their, but close to, so these are not in the truly nano regime. And we are looking now at the nanowires that are smaller than that, because they're not nearly as conductive, okay? But for these nanowires, I found no correlation, virtually no correlation with the diameter, meaning that, you know, once you get, I guess, above 300 nanometers, it doesn't affect the phonon mean free path, okay? Because the phonon mean free path must be a lot smaller at room temperature, maybe at lower temperature. So if I could partner with somebody where we could do it at lower temperature, I would certainly like to do that. But at this level, there's no dependence on the diameter. But there's a very strong dependence on the ratio of band edge luminescence to yellow luminescence. And what we see is that as the band edge luminescence becomes higher, the fraction becomes higher, the thermal conductivity also improves. And that makes a lot of sense because it is also well known that photons will scatter from defects. Okay? And what I showed here is just these 2 points. You see, the thermal conductivity here is going from 4 watts per meter Kelvin all the way to almost 300. And I looked in the literature. The theoretically calculated thermal conductivity of gallium nitride just on the ball modules is something like 400 watts per meter Kelvin. But what most people report about 200. And of course, they're using films that are known to have a high dislocation density. So these materials offer a really nice opportunity to look at the thermal conductivity. We say, look, we don't have dislocations here. Okay? And now, in addition to looking at thermal conductivity, I was also interested in seeing, well, at what point do they fail, and how do they fail? And this is really very preliminary data. I don't understand the mechanism, for example. Maybe it's actually a combination of melting, local melting, and some kind of electromigration, although electromigration has been studied very much in metals, but not in semiconductors. Well, if we're going to go to semiconductor nanowires, I think we should look at things like actual atoms moving under an electron wind. And what I'm plotting here, now this is, some of these nanowires were broken by simply ramping the voltage. So they were not done under steady state. So it's both the steady state as well as those where we just ramp the IV quickly. What you see is that in this case, there is a dependence of the current, not power, but current, okay, and the failure cross-section, meaning that current density is very important, okay? Okay, so now I'm going to show you some more results with the nanopillars. The nanopillars, they already make a p-n junction. In this case, it's a linear p-n junction. It's not a perfect p-n junction, but we're just getting started. And we can, of course, do the PL. You see very nice, high-quality PL characteristics. One of the advantage of the nanopillars, they can be grown under conditions that are optimum for gallium nitride growth, much higher temperature. So we shouldn't get carbon incorporation, okay? And we can start looking at lasing. Now, of course, I was very interested in looking at lasing from arrays because you can now, first of all, they can be vertical. You can think of very interesting games. For example, arranging these nanowires as a photonic crystal. Okay. But what actually happened is that the laser. I don't know if you can see it. You can actually see there's little points here. That's what we're looking at. This is an image. So we have a camera, or we can just have the light going to a spectrometer. You can actually see little points. That's the lattice. That's a very nice regular lattice. But the lines that you see here are nanowires that were popped off by the laser. Okay? And those laze a lot stronger. Okay? And you say, why? Why would they laze a lot stronger? Well, you have to consider that these nanowires are sitting on gallium nitride film. So the reflectivity there is going to be very low. In fact, the light is going to leak out. So it's very hard to get light to be reflected off the nanowire because they're just nanowires grown on gallium nitride. If they were grown directly on sapphire, it would be better. But what we can do is we can just take these nanowires, and I've actually embedded them into PMMA, which of course PMMA has higher index of refraction, so that has to be taken into account. But what we can do now is we can look at individual nanowire, so we can measure its dimension. So this is one of these nanowires that's sort of lying on its side. You can see now that, remember, in photoluminescence, the whole thing glows. But when it's lasing, you can see that there's guiding. Okay? It's a Fabry-Perot cavity, so it guides the light. And what we're interested in is looking at the modes and how these modes will be related to the geometry of that pillar. And in fact, this is the lasing spectrum. And what you see here is, so this is at very low pump energy. You see it's basically photoluminescence. You can see the shifting. Now we're not at 364, 365. We're shifting. It's probably formation of electron hole plasma. Okay, so you see the shift there, and you start seeing modes. And as the pump energy increases, what you see is you start seeing. So here you see these two modes, and now at higher energy you see this triplet and this triplet. If you look at the separations between them, and you use this very well-known equation for longitudinal modes, you see that it works out very close to what we're supposed to get. So what we can say is that we have 2 longitudinal modes and we have 3 transverse modes. I don't know exactly what those modes are. We have to do a calculation to see is it a TM mode or what mode it is, what modes are going to be allowed given how much pump energy we're putting in. But clearly the dimension here is larger than the critical dimension that you can calculate from just optical fibers, very well known. What's going to be the critical dimension to getting just a single mode? And given the industrial refraction of PMMA, I'm getting 130 nanometers. We're above that, so we would expect to have transverse modes. Here's another nanowire. I wanted to show a comparison with just the bulk gallium nitride film. There's a couple of things that are different. First of all, gallium nitride film starts to laze at much higher energy. So the nanowires do start lasing 0.83 million watts per centimeter square. The film here does not laze until we're at 3.1 megawatts per centimeter square. So the energy required to get lasing is lower in the nanowires. Also in the film, you see it continues to shift to lower energy. We don't quite see that shift in the nanowires. And this is just a plot, and I'm just going to go through it quickly. Again, it just summarizes the results that there is lower threshold, and this threshold is really because the number of modes is limited. Not so much because of the spatial confinement and difference in electronic structure, because these are just too big for that. This is some recent lasing from nanowires grown at Sandia. This is the VLS. They also laze. We can look at the mode structure there and understand it reasonably well. Again, you see the guiding. Here, these are much longer, of course. And so, finally, since I have to end, I wanted to show a couple of other things that I saw quite a few talks from people that were interested in charge transfer. We made kind of a platform for looking at charge transfer by using imprint lithography and making silicon nanowires. They make very good transistors. They don't show hysteresis. And they're very sensitive to any charge that gets on it, both in liquids and in gas. And I would love to functionalize it with a polymer or anything that people have interesting ideas to functionalize and look at details of charge transfer. And the second thing, last thing, we've also been doing quite a bit of work looking at how we combine molecular electronics with Raman, particularly because we wanted to see, for example, if we apply a field to a molecule, would it change its Raman spectrum as it should in principle. We're sort of working towards a single particle type of geometry. We're not quite there, but the basic principle of, for example, creating a closely packed array of spheres, which are, of course, very active, plasmonically active, so they give you strong Sir signal. When we substitute the initial molecule, in this case an amine, with thiobenzene, for example, we see a huge change in the drop in the resistance. It's very, very reproducible. And we can now tell with Raman that indeed the molecule is there. And we can also see changes. When we apply high bias, the Raman changes and the electrical response. And that's
You got 50 more slides?
no, that's it. This is the last one. A lot of contributions from different people. Thank you. Sorry, I went on.
Okay, we have time maybe for a question or two.
What about electroluminescence? Have you ever seen electroluminescence from this quantum wires? Or nanowires?
Not yet. I haven't looked for that yet. We're clearly we have PM junctions, so we're doing that right now.
Bi-steps, so we don't see anything.
You know, I'm being a little bit evasive because I think I did see something, but until I see it in a reproducible manner and measure the spectrum, so we're working on it, but I don't have a spectrum yet. So as you can see, the PN junction was not very high quality. I'm not sure why it's not, but we obviously there's some conditions have to be optimized for that.
Let's take one more and then we'll go for the break.
Does any of your nanowires show different temperature dependence of thermal conductivity than that of bulk system? Do you see anything?
Well, the main thing that we see is that in some nanowires we see considerably higher thermal conductivity that's been reported than what's been reported for bulk.
How about temperature dependence?
No, I haven't measured. That's what I mentioned that I would really love to do it at particularly at lower temperature, because I'm sure as the temperature gets lower and the phonon mean-free path becomes larger and gets to the dimension of the nanowire we're dealing with, then we will see a reduced thermal conductivity as compared to bulk. But my setup doesn't have cooling for it.
Let's thank Alec once more. And I have a request. Let's cut the break a little short, so let's take 15 minutes and reconvene 10 to 3, so we can leave early.
French?
Yeah, so French.
Yes. Yes, that's actually where Oh, absolutely. No, absolutely. Yeah, absolutely. I know exactly what well, it's on. I don't know if it's hot. It's very nice. I mean, you can see it off just off right. What I bought it was oh, well, it's no. You look at me. It's still connected. Go.
Your life support is so
it's huge. Okay, all right.
You're saying higher.
I see higher conductivity. How much higher? Well, I think that certainly